Okay, in the second half of lesson 5, we're getting into data distribution and really taking a deeper look at what a standard deviation is and how we use it. So, data distribution is basically just describing the way the data falls, the way the data looks. I wrote cluster. It doesn't really matter your verb or adjective. It's an adjective. This isn't English class. Okay. If I have a distribution that the data looks like it starts, there's a lot on the left, but then it gets little on the right. It's a little bit opposite of what we would think. This is a positively skewed set of data. On the other side of that, we have a negative skew where we have most over here and then less as we go. But what we're going to talk about today is about this, where we have a quote normal distribution. Okay, a normal distribution is a perfect set of data. That's what normally, when you make data, it's going to follow this bell curve. If you ever have heard a teacher say, I'm going to grade you on a curve, they're talking about this curve specifically, this bell curve. Now, the area under the bell curve represents all of the probability. So all of your data is represented on this curve. Everything is here. So that means the sum of that probability is 1, because probability maxes out at 100%, and that as a numerical equation is solid 1. So here's the breakdown of how a bell curve works. 68.2% of the data falls between 1 standard deviation from the mean. The mean is the average. It's in the middle. That's that fancy M that looks a little bit like a U. 95.4% of it is between 2 standard deviations, and then between 3 standard deviations, if you go that far away, 99.8% of your data should fall between there. The breakdown looks like this. So here's the mean, 1 standard deviation to the left and to the right. That's what I mean when I say between 1 standard deviation. So this is 1 up, 1 down. It's between this. The 34.1, that came from me cutting this in half. Okay. Now, the green, the next standard deviation out, 13.6 and 13.6, that came, if I add these 3 numbers, now 1 standard deviation out, and then including this other like 27.2% gets added to that. That's how I get the green one. And the red, now I'm going 1 standard deviation even further, 2.2%. I'm adding all of these numbers together, and that's where I'm getting the 99.8, which leaves, of course, the 0.2% that we don't have accounted for in 3 standard deviations, and that's what we see on this small end. So 0.01, 0.01, I just take that 0.02 and cut it in half and represent it on both sides. Okay. This is an important figure right here for you. We will use these percents constantly. You don't necessarily have to memorize them, but it'd be pretty cool if you did, because it will help you out a ton. Now, let's get to our questions. The weights of 50 football players are normally distributed. Okay, that is important because we can't do this if you don't have a normal distribution. None of this will work if that's not there. 50 football players average 178 pounds with a standard deviation of 8 pounds. Okay, so what we're gonna do on this graph here is basically copy what we have at the top. So here's my mean. 1 standard deviation out. 2 standard deviations, and then plus 3 standard deviations. Over here, I'm gonna have -1 standard, -2 deviations, and -3 deviations. Okay. So this is the same exact setup that we had up top. We're just gonna put numbers with it now. So these football players averaged 178 pounds. Right in the middle, 178. Now the standard deviation of this set was 8 pounds. So if I go up 1 standard deviation, that means I'm gonna go 8 pounds up. 186. If I go up another standard deviation, 194, and then 202. Those are the weights of those people. Now on the other side of it, we're gonna go down a standard deviation. So we're gonna go down 8. Whoops. You don't suddenly become negative weight. That's not how that works. Although that would be cool. That would really help my diet. Okay, so these are the values. The mean is this. If I go up a standard deviation, that means I go up 8. If I go down, that means I go down 8. Okay. Now, it would be helpful if we write in these percents. 34.1, 34.1, 13.6, and then 2.2. And then lastly, we have our little tail ends of 0.1. Having this framework and this data copied in there is going to make this much easier. So now let's take this and let's go to answer the questions to the right. What percent of the players weigh between 178 and 194? So 178 is here. I'm including this, and 194 ends there. So what percent of the players fall between? Well, let's take these 2 percents and add them together. I'm gonna say that is 47.7%. What is the probability that a player weighs at most 170 pounds? Okay, so we're capping at 170. 170 is here. And at most, right, that's the maximum. So I'll take all of this over here. What is the probability is another way of asking what is the percent. It's the same thing. So I'm gonna take these 3 values, add them together, and I'm pretty sure that's 15.9. 15.9%. What is the probability that a player weighs less than 162 or greater than 194? Okay. Remember, or is an add statement, and is usually multiplying. So if I'm saying or, I'm going to add some percents together. The probability that the player weighs less than 162 or more than 194. Less than 162, that's over here, or more than 194, that's over here. I'm adding these blocks together. So 0.1 plus 2.2 plus 2.2 plus 0.1 equals 4.6. Okay, and our last one is slightly different, slightly. How many players weigh between 170 and 186? So we're gonna start the same. 170 is here, and I want 186. So how many players are in here? Well, first I need to find the percent. Add them together. You get 680, 68.2. Okay. And that makes sense. That's the figure between one standard deviation. That's this value right there, between one standard deviation. But it doesn't ask the percent anymore. It asks how many players. Okay? So, how many players did we have total in the problem? 50. There were 50 players. I need to figure out what 62.8% of 50 is. And how I do that, I can't like put this in my calculator. My calculator says if I multiply 50 times 68.2, I'm gonna get like 3,000 something. And you can't tell me that 3,000 players weigh between if we only have a max of 50. So we need to convert this into a way that our calculator likes it and we can use it. How we do that is we take the decimal point and we move it 2 to the left, making this into a decimal, 0.682. Now I can multiply 50 times 0.682. And I get something. 50 times 0.682, 31, 34.1. Now let's get real because we can't have 0.1 of a player, right? So how many players? About 34. If I played on a football team, I would be that 0.1. Okay, like I'm just nudging you a little bit, but I'm not a full contributing member of that team. I would get crushed. Okay, that's why I don't do that. All right, and let's do maybe one more example of this. A set of 120 test scores were normally distributed, that's good, with a mean of 82 and a standard deviation of 5. Okay, so label the picture the same way we did before. It makes everything easier. My mean was 82. And my standard deviation was 5. So if I go up a standard deviation, I'm gonna go up 5. And if I go down, that means I'm gonna go down 5. It's the funny number. Is that still funny by the time you're watching this? It's funny. Okay, put in those percents. 34.1. 13.6. 2.2. I hope that 6-7 thing is gone. I don't want to raise my child in a world where they have to say 6-7 and then like violently throw their hands and then like slap their buddy in the face. I don't know what you guys do. You do dumb stuff. Okay. All right. There's my data. There's my distribution. I'm all set now to answer. What percent of the scores are between 72 and 87? So 72 is here. 87 is there. What percent lives in there? Well, that's going to be this plus this plus this. And I don't want to do that in my head. So it's 81.8. So a good chunk. Most of the data, definitely. What is the probability that a score is bigger than 177? So bigger than 177. If this is the floor, I want everything bigger than it. I'm gonna add 34, 34, 13, 2, and 1, and get all those decimals and stuff in there. And I'm gonna say that there is 84.3%. Is it 0.3? I guess it is. Okay. I'm gonna trust myself that I can add numbers in the past. What is the probability that the score is less than 82? Okay, so I want 82 and below. And what else do I want? Greater than 92. That's gonna be 52.3% if I add together all of those percent things. And then our last one. About how many students scored outside 2 standard deviations from the mean? Okay, so we're talking outside 2 standard deviations, which means this is 1 standard deviation away, this is 2. Outside of that would be over here. And then 1 up, 2 up, outside of that would be here. So I need to figure out the percent. Looks like it's gonna be 4.6%. So I'm gonna write that over here. Now, again, this is one of those ones that says, I don't want the probability, I don't want the percent, I wanna know how many students. So, about 4.6% of the students, sure, but what does that equate to? How many are there? Again, our calculator won't do this. So we need to take that decimal, we need to drag it 2 places to the left. And my new decimal is gonna go there. What do I have to drop in there? A 0. So, this as an equivalent statement is 0.046. 6. Now, how many students took this dang thing? I think it was 120. Yep, 120. I'm gonna take 120. I'm gonna multiply it by this 0.046, and that is gonna tell me how many kiddos. 20 times 0.046. I got about 5.52. Okay. All right. Now, about how many students scored outside. Again, it's about. It could round right. This is like right in the middle. So you could say 5. You could say 6. Or you could probably say either. About 5 or 6. I will take both. And my answer is I wrote 5. If I'm looking at this now, I'd probably round that up to 6 because it's more than half. But really, it's about 5 or 6. Not about 6 or 7, about 5 or 6. Okay? Good. Thank you. Thank you for what news you have to give me. Okay, so take some time. You have 2 more of these. Give them a shot. See what you can do.